Okay, so the problem for this week is monotone matrices. As you can see, this is for to understand how do we write divide and conquer algorithms. This is taken from CS 170 Fall 2020 Homework 1. And yeah, I encourage you to pause the video here for a minute and read the question, make sure you understand it, and then we'll go over it together. All right. Um, okay, so I'm assuming by now you've paused the video and read the question, understood it, and we'll go over it together now, right? So basically for a monotone matrix, it has two properties, right? Number one, no row of the 2D matrix has duplicate entries. And number two, for each subsequent row in the monotone matrix, the minimum value occurs at an index greater than the index of the minimum value for the row above it, right? So over here, if we just kind of label the rows 0, 1, 2, and we label the columns 0, 1, 2, 3, 4, and 5, we see that the minimum value for row 1 occurs at index 2, right? It's this 2 right here. Now, for the row above it, the minimum value has to occur at an index that's strictly less than the index of this row, right? So that occurs at index 0. And similarly, for the row after it, the minimum value should occur at a column index that's strictly greater than the column index of the minimum value for row 1, right? So for row 2, it occurs at index 5. So this is a classic example of a monotone matrix. And yeah, also I've made a few test cases for us that I'm going to clear this. I've made a few test cases for us to go over to sort of get a better idea of monotone matrices. And we'll also use these test cases to finally check our algorithm at the end, right? Also, the output format for this is pretty standard since it's ambiguous in the question. Let's just say that we want to return a list of the minimum values of each row, right? So for test matrix 1, I just used the same matrix that was given here. And as we can see, the minimum of each row is 1, 2, and 0 respectively. And so therefore, the expected output is this list that's 1, 2, and 0, right? Similarly, for test matrix 2, it's 1, 2, 3, 4, and then 6, 5, 4, 3. So similarly, the expected output will be 1 and 3, right? And for test matrix 3, our minimum values are all ones along the diagonal. So the expected output is going to be this list of ones, right? Okay. And lastly, and most interestingly, I've made this kind of, it's not really a trivial input, but this is really to see the difference between an efficient approach and a naive approach. So I've made this test matrix large that whose size is 10,000 by 10,000, so 10,000 rows by 10,000 columns. So it has 10,000 square entries. And what I've done is along the diagonal of this matrix, we've made all the values 0, right? So similar to this, to test matrix 3, how along the diagonal all the minimum values occurred and they were all 1. I've made this test matrix large of 10,000 by 10,000 ones, and then just edited all the diagonal values to be 0. So the expected output for this would just be all the values that occur along the diagonal, right? So the values that occur at 0, 0, 1, 1, 2, 2, 3, 3, all the way up until 9,999, 9,999, right? Okay, so that's the expected output of this, a list of 10,000 zeros, one for each row. All right. So I hope you've understood the test cases. I hope you understood what the question asks of us. And before we get into writing an efficient approach, let's just think about how we can write the naive approach for this algorithm. Okay.